Hi everyone and welcome to a new video about control system topics, and we're continuing with the subject of Nyquist stability criterion and for a system with a time delay. In this example we will again look at the calculations and verify our calculation using simulations, and this is our example number 3. Now in this example we have some practical situation. We have this level controller. So we have a pipe which will source a liquid here through a valve, and that will be controlled by a actuator, and that actuator will of course give the signal to the valve by taking the signal from the float. So we have a float here which will give the signal to the actuator will command the valve, and the valve will of course determine the inlet of liquid here, and it will determine of course the height. So the level, which actually the output is the y here, so this is the height of this tank. There's also a command here, which is actually the set point. We have an actuator, we have a delay here due to this distance, because the valve is here and the actual liquid is coming out this pipe at this point. So there is a distance between the valve and the actual output, so that means there is a delay, and it will of course result in delay time. Since the velocity and also the cross-sectional area of this pipe will determine the volume, that will also determine the time delay using this d, the distance. This is for example in centimeters, and the flow rate is cubic centimeter per second, and that will of course determine your time delay in seconds. We have the flow that has also its own dynamics, and the tank has own dynamics. Now the list is shown here for the system. The actuator is a first order system, is shown here, so which is the A, and the tank is also a first order system, which is the G, and there is also a float Fs, which is a second order system, and the delay here in this case is given as a general expression. Now the question in place here is different than the former exercises, former examples. In this case we would like to calculate the maximum allowed delay time, T of D, to have a stable closed system. So there is no controller gain involved in here. Only unknown and only required value is actually the maximum allowed time delay, and we will use again Nyquist stability criterion for this exercise. So what we do is, as we did also in the previous examples, we start with the step 1, determining the loop gain LS of the system. Now the loop gain of the system can be determined by starting at a specific point and make a full circle. So if I just start here and I make a full circle, I have the loop gain is A times D times G times F, and it's actually shown here, and I've purposely used different colors to recognize the different elements in this configuration more easily. So the loop transfer function is this one. If I substitute all those values, I have this, and I've purposely placed the delay expression at the end. That will be easier to follow in the next steps. Now in the analysis, in the frequency analysis, I would like to convert the expression shown here in the S domain to the j omega domain. So that's actually also what we would like to do. And what I also do is 2 steps at one. I will also a little bit simplify this expression, because there is a 1 and a 10 and 8 in the numerator, and I will make that at 80, and I will place this expression for the delay also in the numerator, and I will have this four parts, and I will place them next to each other in the denominator. So the expression, convert the loop gain expression into the j omega domain, that will be like this as shown here, and I've only replaced the S by a j omega, and I've just simplified this by 80, and I place this expression of this e to the power minus TD S, and I S of course replaced by j omega. So this is actually the expression. Now, the next step is what is actually in this case. The next step in this case, the situation is a little bit different than the former 2 examples. What I need to know is of course the TD. Now for that I can use the magnitude and the phase of our expression for the loop transfer function. Now if I want this parameter TD, I can also see that there is an omega which is also unknown, so there are 2 unknowns. If I take the absolute value of this one, then this expression will be just 1 and it will drop out. So that it will be handy to start with that one first. So what I mean by that is, if I have a stability problem, I will need to calculate the magnitude and also set that to 1. That's actually just at the edge of stability. And I also need to have the argument or the phase of the loop transfer function. I have to set that equal to minus 180 degrees and then calculate the required omega. So I will start first with determine the critical frequency for stability, but then using the absolute value of the loop gain, and I will set that equal to 1. Now you can see why that happened, why this is handy, because then this will be gone. There's just unity that has a length of 1, and I have just AD in the numerator, and I have just the length of these 4 parts in the denominator. Now if I just set that equal to 1 and solve this for the smallest possible value of omega, I will get the critical omega value, which is 1.23 radians per second. Now I will now use this in the next step. Since I know this and I have now a specific value for omega, I can now say, okay, for this transfer function at this frequency, I know what happens for the stability, because this is the edge, and that means if I have a unity gain and then also a phase shift of minus 180 degrees, I will determine the maximum allowed time delay. So the next step is, step 4 is actually determine the maximum allowed time delay for stability, but then using the argument of the loop gain, which is also the phase shift expression. We will use argument of the loop transfer function. I will substitute 1.23 radians per second in that one and set it equal to minus 180 degrees. But in this case, we need to be a little bit careful, because the expression in here is given in e to the power minus jtd omega, and this is in radians. So I have to also set this equal to a radian unit. So this is minus 180 degrees, of course. And if I just substitute the value and also minus 180 degrees, but what I need to know is this expression, but then minus pi radians. So this here is actually the expression which is not equal to minus 180 degrees, but minus pi radians. Now, solving for the smallest value, positive value of TD, we will get, if you just solve this, which you can see is, I would just substitute 1.23 here, 1.23 here, 1.23 here, 1.23 here, and also there. So there's just a quite easy expression, and I have just only a known TD, and that will result in a value for TD, which is 0.95 seconds, and it is actually our maximum allowed delay. So I have already answered the question. Maximum allowed time delay is 0.95 seconds. Now you can also say how long can this be, this distance from the valve all the way to the out of this the pipe. Now that depends on, of course, your flow rate. If your flow rate, of course, increases, you can also increase this. That depends on your flow rate, so velocity. Again, remember, do this with a radian and not in degrees, because that is given in radians. So again, use this expression and then go from there to the expanded expression for the phase of the loop gain. Now, this is already our calculation, so we are actually done with the calculations. Let's now verify our calculation using the simulation in the next step. So let's look at the both plot of the loop gain without and also with delay time of 0.95 seconds. So this is our body diagram. What you see is the following. We have the blue line, which is actually the situation L0, which is the loop transfer function without delay, and L1 is the one with a delay of 0.95 seconds. Let's look at this first, the blue line. What you can see is I just look at the purposely at the minus 180 degrees, And then if I go up, I can see that this is the orange line and the blue line actually coincide. So there's actually just one line actually looking, but you have actually two lines here. And if I go up, I can see that there's approximately here, which is maybe minus 8 dBs, but it is not 0 dB. So that means actually there is no stability problem. There is no, we are not at the edge. But if I now look at the orange line, and if I now look at this label, I can see that this is at minus 180 degrees phase shift is a frequency of 1.23 radians per second, which we have calculated as the critical frequency. If I go up at the same frequency, I can see that the magnitude of this line, orange line, is almost 0 dBs. That means I am at the edge of the stability. That means this time, which is maximum allowed time, is correct. So this is actually the situation which is in this case verified using a Bode diagram. And this is for this system with the maximum time delay. And this is our critical frequency. And this is a situation where we don't have the time delay and where we have no problem, and we can add some gain. Okay, let's look at also in the Nyquist plot of the loop gain without and with the delay time, of course. So this is our Nyquist plot. The blue line is again the system without the delay, and the orange line is the system with delay. Now, which you can see here, this is the situation where you have a label, and as you can see, this is just a plot for the situation where you have no delay. Now, the orange line here will have a delay, and exactly the maximum delay will also make this real part almost minus 1, because the imaginary part is almost 0. That also is confirmed, and you can see that the frequency is 1.23 radians per second, which is what we have calculated. So that also confirms this. What you also see is here, this is for the blue line plot, you can see that the phase margin is 66.8 degrees. What you also see is that the delay margin is 0.95 seconds, which is actually this delay. So we can actually add this much delay until we reach our unstable region. So this is actually the conclusion here. So this again, the critical frequency is 1.23 radians per second, and the real part is almost minus 1. That means there is no room for additional loop gain. Okay, so if I now look at the step response of the closed-loop system without the time delay, what you see is it is a stable system. We have a huge overshoot, and the setting time is also quite large, 7 seconds approximately, but it is stable, so no problem in terms of stability. Now, if I look now at the unit step response of our closed-loop system with a time delay, which is now 0.95 seconds, I have the following. And that looks like an oscillation, so we have now again the edge of stability. So if I have a time delay of 0.95 seconds, I will change my system from a stable system to a marginally stable system, and then a little bit larger than this one will make my system unstable. Okay, that was it for this example. We have specifically looked at the system with a time delay problem. So we have now determined the maximum allowed time delay of 0.95 seconds. This was not a that difficult example as the previous two examples, but the methodology or the steps are similar. We need to check the minus 180 degrees and also the unity gain condition for our Nyquist stability criterion. I hope this clarifies the situation even more with this different example. I will try to add more videos or other topics also, so keep in touch, and if you have any questions or comments, please let me know. Take care and see you next time.